we've talked about two circuits that oscillate. LC circuits oscillate forever. RLC circuits oscillate, but they actually decay due to the resistance. Now we're going to get into more complicated AC circuits, circuits with all the different elements. And you could keep up with the voltage, the oscillating voltage and the oscillating current in each element, but then that's a lot of them to keep up with. When they get out of phase, it gets very complicated. So in AC circuits, we like to study average values to simplify things. Things, what an awful choice of words. But rather than keeping up with the oscillations around every component, every voltage, every current, we will just consider the averages. So as our first example, let's just think about a resistor with an oscillating current going through it. We've actually played with something like that before, and here it is. When we were thinking about power generation and how resistance depends on temperature, we did some demos with this little heater. And this is, remember, it's this nichrome wire all coiled around to have a large resistance around this little ceramic holder. And we pretended that it was under DC voltage and DC current, but actually it's plugged into the wall. It's actually under AC. So the current is actually going back and forth at about 60 hertz. The voltage is about 115 volts, and I forgot what the current is, whatever we said it was last time, is about right. So the question is, how should we describe this? What kind of average should we use? Well, we could start looking at the different possibilities. Here is the volts, the delta V as a function of time. And if we plot it, it's just going to be some sinusoidal oscillation, and therefore the average is 0. So that doesn't seem like a very good choice. We could plot the current versus time. Current versus time, along with the voltage, oscillates. It spends just as much time going this way as it does going that way. It oscillates around 0, so the average is also 0. So that's another case where the average doesn't seem to make a lot of sense. In fact, from these two, you'd say, well, if the average is 0 and the average is 0, maybe we can just conclude nothing happens, and then we're done with AC circuits. That's nice and easy. Well, clearly, though, something happens. When I get close to this, it's very hot. Okay, something is going on. Let's plot the power. The power versus time. Now let's see. P, if we do it in terms of current, it's I squared R, and R is a constant, so you got to square this. Well, this will square and be positive, and the negative parts of I will square and be positive. And if we were to do V, the power is delta V squared over R. Again, you square this, it's all going to be positive. So if we plot the power, it will be something like this. It'll be a sinusoid, a squared sinusoid, that's always positive. There are moments where the power is 0. Right? Just like there are moments when the current doesn't flow. Here, the power does hit 0, but it never goes negative. This is my poor chalkmanship here. It's always positive. Okay? The average of the power is also greater than 0. And an average like this is what we need to be calculating, okay? Because we know there really is something generated. The whole thing isn't just making 0. The oscillating current and the oscillated voltage, even though their average is 0, something really does happen. It generates power. The power's average is not 0. So the point of this is simply we have to be careful with what average we use. Okay? You don't want to use always just the simplest average that there is. Okay? So we could then say, let's just use the average. If we want to think about currents, current. But we've already ruled that out. The average current is 0. We don't want to use that. We could use, what about the maximum current? We could use the amplitudes. Well, the problem with using the amplitudes is it's essentially hardly ever at the maximum value. doesn't really represent an average, it represents a peak. So we don't want to use the maximum. The thing we want to use, which you've probably heard of, is the RMS, the root mean square. So the RMS. So defining and using the RMS is the first step towards coming up with a way to write the equations in terms of averages where you can treat them like the DC equations to some extent, not completely like the DC equations, but in a situation where you have sort of the power is I squared R, if you use the RMS for the average power and the RMS for the current, you'll be able to still just say the power is I squared R. You won't have to think about all the little oscillations. So let's see how we're going to get it. Well, we would write it then, it would be the IRMS would be, it is literally what it says. It is the root, the square root of the mean, the average, and square. So you square it. You take the instantaneous oscillating value, you square it, that way it's always positive. You take the average of it, and then you want to get back to the original units, so you take the square root. Let's see what it is for a sinusoidally oscillating current, which is what we're essentially, we're always going to have, right? So if I is I max sine omega t, so let's square it. All right, that's I max squared sine squared omega t. All right, let's take the the mean. Well, I max is just a constant value in front of the sign, so the average of I max squared is just I max squared. That's just like a number like 4. It doesn't depend on time. The average of sine squared is a half. So if you plot yourself a sine squared or a cosine squared over a complete cycle or over many cycles, you could do the integral to show it's a half, you could geometrically show it's a half, you could stick it in a computer and find that it's a half, but it is numerically equal to a half. Okay. So we got the square, we got the mean, now we just need the root. And well, square root of this is 1 over the square root of 2 I max. So for a sinusoidal current, and pretty much everything we're going to do is going to be sinusoidal, the IRMS is just the amplitude of the oscillation times 1 over the square root of 2. Same thing for the voltage. We could have done all this for delta V. The RMS delta V is the maximum delta V times 1 over the square root of 2. So we'll be using lots of RMS currents and voltages as we analyze AC circuits. So now let's look at our first circuit, our first AC circuit, the AC driven resistor. We could draw it like this. We have a new thing, an AC power supply. So a battery applied a set potential difference, a constant potential difference between 2 points in a circuit. This just applies an oscillating potential difference between 2 points in a circuit. We might describe it like this. Delta V, where the little script V means it's a function of time, is delta V max, the constant amplitude, times the sine of omega t, some oscillation. That might be what's coming out of this power supply. And then it goes up and to a resistor. So the resistor is simply being driven by an AC power supply, which is exactly what we have here. So here we have the wall is applying an oscillating delta V at about 60 hertz, 115 volts to the nichrome wire, which is just a resistor. Current's flowing back and forth, voltage is flowing, or is oscillating back and forth, the potential difference. Okay, so let's think, how do we describe that? Well, the power supply applies this delta V. There's some voltage drop across the resistor. Together those are equal. They're equal to 0. Their sum's equal to 0. So we know that then the little delta V that's oscillating time equals IR. So the current must also oscillate in time because the resistor is constant. So we can then say I is the oscillating delta V over R. And we could then write it out. Well, this is delta V. So it's delta V max, the amplitude, over the constant r sine omega t. Okay? So we get the simple result for this circuit that I, the current, oscillates in phase with the little delta V. So that's really the result we're looking for. The potential that's applied is oscillating at sine omega t. The current, since they're proportional, comes out to the same thing, sine omega t. So if we were to plot the applied delta V coming out of the power supply like this, and then we were to plot on top of it on this axis I, they would be right on top of each other. Both sinusoids. Like that. Okay. Now, we could also think of this as in terms of the RMS, right? So maybe thinking about the power is a good way to start. So we know that power, let's think about the average power. The real power being generated is fluctuating. Let's go straight ahead and think about the average power. Well, we know that power is I squared R. We know that. So it would be the squared R. It'd be kind of that average for those two things. Right? Well, we know that the resistance is constant, so that would come out. It's surely the average of little I squared, of this oscillating I squared. Well, we know that's really some big I max sine omega t. So you could write that as I max squared sine omega t squared, but the average of that is a half, so you could put a half in front of here. And then the R is still there. The average of R is just R. So hopefully you can see what we did there. I max is this thing right here. We squared that. We squared sine omega t. That's where the half comes from. So P average is that. But then if you look, you see this is 1 over the square root of 2 times I max times 1 over the square root of 2 times I max. That's the RMS. Right? So we get that P average is I RMS squared times R. The square root of that is that this is 2 IRMSs times each other if you go from I max to IRMS. So you can see this is a case where when we do averages and RMSs, it looks like the DC equation. P is I squared R. You could do the same thing for P equals V squared over R. So that's why those RMS averages are useful. They keep you from having to keep up with 2's and square roots of 2's. Now we will consider an AC driven capacitor. So again, we have our little AC supply right across the capacitor C, and the little oscillating voltage is delta V max sine omega t. Okay, well, the delta V we're applying across the capacitor, we know has to be equal to the charge on the capacitor over its capacitance. So we can start plugging in things. Let's solve for the charge. So Q, the charge on the plates that can vary in time, is now C times delta V max times sine omega t. And in circuits, we usually care about current, not about charge. So if we wanted the current in the circuit, we'd take the derivative of this. So I, the current as it varies in time, is dq dt. So the derivative of sine is cosine. You pull out an omega, you have C omega delta V max, cosine omega t. So we apply a voltage, we get a current. We can look at them, we see they're both sinusoids, but there is a phase difference between them. So if we plot now time, and here I'm going to plot two things. First, I'm going to plot the sine, or I'm going to plot the voltage. We're driving with a sinusoid, so if we call this the origin 0, a sinusoid we know starts at 0 and does something like that. So this is delta V there. And then the current we derived is a cosine. So we know it starts high and goes low. So it's going to start up here and it's going to hit 0 when that is a maximum, and minimum when that is 0, and 0 when that's there, and this when it's there, like that. Where this is I. So since one is sine and one is cosine, they're out of phase by 90 degrees. And here we get that the current leads the voltage when you have a voltage-driven capacitor. And by that I mean, if we were to watch time go this way, the current has already peaked and coming down, and then the voltage is just starting to peak. And the current has already gotten back to 0, and a little bit later the voltage gets to 0. So sometimes it's confusing looking at those graphs, who's leading whom. But in this case, the current leads the voltage for a capacitor circuit. And the voltage you apply and the current you get are out of phase. And that's different from the resistor. When you just drive a resistor, current, voltage are together. They get out of phase when you start using other elements. Now let's remember that in AC circuits we can get pretty far by just considering the amplitudes. So for the AC-driven capacitor that we just dealt with, we found that it had a current as a function of time that basically looked like the capacitance times omega times delta V max times cosine omega t. But if we just wanted to think about the amplitude of the current, it would be this. It's an oscillating, it's a sinusoid with an amplitude, C, capacitance, omega, delta V max. So we could also write delta V max, the amplitude of the voltage that you apply, equals, let's see, this would be equal to I max is this, so delta V max would be I max over C omega. So that kind of looks like Ohm's law, right? Equals I max times 1 over the capacitance times omega. So this thing is like an AC resistance. If you're willing to not worry so much about all the phases and everything, if you just want to know the amplitudes, if I apply a 1 volt peak-to-peak voltage, what peak-to-peak current will I get? You can actually apply just a standard what looks like Ohm's law. So this thing that looks like a resistance, it has the units of resistance, but we call it the capacitive reactance. And big X is the symbol. So XC we define to be 1 over the capacitance times omega, which does end up having units of ohms. It is really a resistance. It really does work in this formula. It just shows you that a capacitor is different from a resistor. A resistor has a reactance. It's just the resistance, right? For that, it's just R, and it's constant. But for a capacitor, you see that it depends on the frequency, right? Its reactance, or its effective resistance in a circuit, depends on how fast the circuit is moving. It actually makes sense. If you think about really low frequency, you have a capacitor in the circuit here, and you take the frequency essentially to 0, you're talking about going essentially to DC circuits, very slowly varying that frequency. Well, this is an open circuit at DC. Right? There's basically nothing here. So its resistance should go very big. Well, sure enough, the capacitive reactance goes to infinity when you get the frequency really low. When you have the frequency really high, it's constantly charging and discharging, charging and discharging. So it's like it's not even there. Right? So all the very fast charging, discharging, basically then the frequency is very high, the capacitive reactance is very small. So that's what's unique about capacitors, and in a minute you'll see about inductors, is that their behavior in the circuit depends on the frequency. And now for the AC driven inductor. Let's see, so again we have our AC source here, and now we're going across an inductor L, and this is again delta V. The voltage as a function of time is delta V max sine omega t, what's going to happen? Well, let's not get into it too much. Let's say delta V, the voltage across, has to be across the inductor, so it has to be equal to L di dt, according to the freshman textbook. And then we start plugging in, solving for things. This is, of course, delta V max sine omega t equals L di dt. And to solve this one for the current, you always want to get to the current, you're going to need to do an integral. So let's see. So we're going to keep di over here and put everything else on the other side. The dt comes over, the L comes over. It's delta V max over L sine omega t dt, and then integrate both sides, and you get that the current, we aren't dealing with boundary conditions at the moment, these are just sinusoidally oscillating things. The current would be the integral of this is negative cosine, and you divide by an omega, so minus delta V max over omega L. The sine became a cosine omega t. So there's your oscillating current, delta V max over omega L, and it's a negative cosine. So let's now look at our plot of the delta V you applied and the current response in time. So the delta V you applied is a sine like that. And this time, the current is 90 degrees out of phase again, but it's a negative cosine. So it starts down here like that, and then it's going to come up and hit 0 when that one is there, and it's going to hit its max when that one is at 0, and then it's going to do something like that. Like that. So this is a horrible choice here. So delta V is right there, and I is right there. So again, they're 90 degrees out of phase, and the current lags the voltage this time. And you can see why. Here at time equals 0, we move along. The voltage is already going up to peak, and the current is still stuck negative and making its way up to peak. So our current is lagging the voltage by 90 degrees or pi over 2, whichever you prefer. So it sort of does the opposite of the capacitor in that sense. It gets them out of phase just in a different way. So again, if we don't want to worry about phases in AC, let's just consider the amplitudes. So if we go back, our current in the AC-driven inductor was equal to minus delta V max over omega L cosine omega t. And that's just a simple sinusoid. So this is I max. I max is, and the negative sign also really is just a phase issue. So the maximum, or the amplitude of the current oscillation is delta V max times omega L. So if we equate those and bring the omega L over, you find delta V, its amplitude, is equal to omega L times the current amplitude. So again, this is like an AC resistance, because this looks like Ohm's law. And if you work it out, it actually comes out in ohms, omega times L, the frequency, natural frequency, times the inductance of the inductor. So we define the inductive reactance. To be XL equals omega L. So, like the capacitor, we can now think about it physically. If you're at really low frequencies, then if you're at really low frequencies, your current that you establish may be changing and making a B field, and making a B field that changes and causing induction. But if the frequency is low, it's not doing it very fast. So it doesn't cause much induction. So that's why this doesn't have a lot of resistance or a lot of reactance to the circuit. If your frequency is really high, then the B field is changing fast, more induction, more back EMF, and a bigger effect. So that's why the inductive reactance is linear with frequency, which is the opposite of the capacitor. So we have three elements. Resistor doesn't care about frequency, the capacitor is inverse with frequency, and the inductor is linear with frequency.